Yeah, good morning, Mahdi. How are you?
Good.
Okay.
Thank you.
So let me share the slides. Everyone again. Okay. So I hope the slides is visible to everyone. Hold on.
Yes.
Right. So last Tuesday, we have started Chapter 1, Introduction of Electrochemistry and Concepts. So we have briefly been introduced on the concept of electrochemistry. What does it mean by electrochemistry? What would be the aspects that we should consider when we're dealing with electrochemistry phenomenon? I think we also discussed a bit on the differences between electrolytic cell and also galvanic cell. This is, of course, just a revision for you guys, because for electrolytic and galvanic cell, you guys have learned it during your high school or probably during your undergraduate level. And there's also another things on electrochemical cells, the requirement, what would be the components of electrochemical cells. We are talking about interface. We are also talking about electrolytes, notation, electrodes. So remember that for electrodes, we have three different electrodes noted by working electrodes. Working electrode is used as a electrode of interest, which in this case, if you want to study the behavior of a metal, then this one will be your working electrode. We also have counter electrodes or auxiliary electrodes that is used to measure current, and normally this counter electrode will use non-reactive electrodes such as carbon, graphite, platinum, and whatsoever. Okay, and the last one we have reference electrode. So reference electrode, the function is actually to measure potential. Then we have different kinds of reference electrode, ranging from saturated calomel electrodes, standard hydrogen electrodes, silver chloride, and whatsoever. Okay. Right. We also have looked into electrode process. How does the electron transfer, electron donation occurs, and other things? These basically have a relation between redox, which in this case oxidation and reduction process. Okay, and we also have gone through fast and slow process. I hope you are able to understand that for fast process, this is always related with the phenomenon where the more reactive metals will experience oxidation at anode, then the process will be faster. Meanwhile, for a less reactive electrode, then this one will be considered as a slow electrode process, because it cannot like actually produce the electron, but instead it will consume the electrons to proceed with the reduction process. Right. So today, basically, we are going to look on electrochemical potential. So remember, last Tuesday, I've told you that the overall cell potential, or E naught, will be calculated using a formula as this. E cell is equals to this one. E cell is equals to E naught cathodic minus E naught anodic. Okay, and if you notice over here, this notation is actually stands for standard condition. Standard condition meaning that the process of electrochemistry occurs at pressure of 1 atm. Okay. Temperature is equal to 25 degrees C. Concentration of electrolyte is equals to 1 molar. So apart from this, then we can consider it as not in the standard condition or non-standard condition. Then the formula that we are going to use is of course known as Nernst equation. Okay, so what does Nernst equation tells? Nernst equation actually tells you that in any non-standard electrochemical process, the potential is actually affected with the activity or the concentration of reactant and also product. That is why you can see over here for the Nernst equation, the formula noted over here is E cell is equals to E naught cell plus with 2.303 RT over NF log concentration of oxidation over concentration of reduction. And sometimes you can see this as product over reactant. Okay. Wait. I think someone wanted to join the lecture. Okay. I hear a voice. I mean, probably from. I think Franklin. Franklin, can you mute your mic? Very sorry. Okay, thank you. Well, again, as I said, for non-standard condition, we will consider Nernst equation in order to calculate the overall cell potential, which in this case, we still consider the standard condition over here. This is actually the standard condition. Standard E naught cell. And then the rest is actually the parameters. So there's a lot of variation for Nernst equation. Sometimes you can see 2.303, sometimes you can see 0.0509 and whatsoever. But the most important thing is if you look over here, if you use a log, then the values, the set parameters over here will be 2.303. If you use ln, then this one is 0.0509. Okay, so that's only the difference. I mean, well, also if you use 0.059, is always like over n, not together with RT or whatsoever. Okay, and sometimes you will notice over here the symbol sometimes can be positive, sometimes will be negative. This is just mathematical representation. If you see it is in negative or subtract symbol, then it is actually will become opposite to each other. Okay, so I think throughout few years of teaching this course, still I saw students are a bit confused with the Nernst equation or formula. They are not sure which one is correct. But as I said, all variation of Nernst equation is the same except the modes of mathematical representation that they use. Either they use log, either they use ln. Plus or minus is just opposite direction and others. Okay. The potential that develops in a cell is a measure of a tendency for reaction to proceed towards equilibrium. Okay. So at any electrochemical process, the process is having an aim to have or to achieve equilibrium state, right? So that is why I think the overall cell potential must be calculated, as this will be a good indicator to know whether process have reached equilibrium or not. Okay. Right. A is actually refers to activity. Some may call this as concentration, but activity can be, apart from concentration, it can be also for pressure whatsoever. So that is why we call it as A. And gamma is actually activity coefficient, gamma, and X is actually concentration. So standard reduction reaction for all relative to hydrogen reaction, okay, at 298 Kelvin, so 298 98 is actually equals to 30 degrees C, with unit species and pH equals to 0. So you know that when you look at this condition, it is considered as non-standard condition as of the temperature and also the pH. When we use the concentration in the Nernst equation, but actually, as I said, activity will be the most appropriate form. The activity of a species can be defined as the ability of the species to participate in equilibrium reaction involving itself. Okay. So that is why in any cell potential calculation for non-standard condition, we will actually consider activity as the active species that play into a role that affecting potential and whatsoever. Okay, right. So this is actually what we have known. The standard potential E cell is equals to E naught cell minus E naught cathodic minus E naught anodic. Okay, and bear in mind that if you use this formula, okay, it must be in standard reduction formation. I mean, like the equation must be as sorry. The equation must be in the reduced form, Fe 2 plus 2 electron equals to Fe, for example. Okay, then this E naught for iron is equals to minus 0.4 volt. When you use this formula, okay, remember that you didn't change the symbol. I mean, like, it will be anodic. I mean, this will be anode, then you just change to make it positive. It is actually not correct. Okay. For hydrogen, the E naught is actually equals to 0 voltage. Imagine if you have a pairing, or if you have a corrosion of a metals in acid, Fe, HCl. Okay, so this will be anode. Reason why because the potential value is negative, and this can be considered as the most reactive metals, and hence it tends to become oxidized easily as compared to hydrogen, hydrogen gas. The overall E naught cell equation will be 0 minus 0.4, then you get 0.4 volt. Okay, all right. So the other two equation is actually known as Faraday's equation. What is Faraday's equation? Faraday's equation actually relates free Gibbs energy with potential. So that is why you will see over here, delta G is equals to negative NFE. N is actually valency, number of ions that will be involved. Okay? And then F is actually Faraday constant. Faraday constant is equals to 6,500 coulombs per mole. And then cell is actually standard cell potential. Then the other representation will be free energy, delta G, is equals to negative RT ln KE. Okay? So you'll see the importance of all these three equation is that this is actually the basis equation, okay, to derive Nernst equation. Okay? Later on, you will use this to define or to probably propose the Nernst equation. Right. So basically, this is just an example to look at the activity, but of course this one is far more physical electrochemistry. A metal electrode is half immersed in a solution that contains quinone and hydroquinone, which not the activation, the activity are AQ and AQH2 respectively. The acidic activity of the solution is AH plus. Derive the relationship between electrode potential with the pH. Okay? So as I said, this is just an example how you can use the experimental condition in order to relate it with Nernst postulation. So you see over here, you know that quinone will be reacted with hydrogen ions to produce hydroquinones. So using the electrochemical potential term, then you will actually add on mu. So mu is actually the ions mobility. Okay. And using chemical potential term and electric potential term, then you will into this form, and finally you can get into a Nernst representation by rearranging which one will be product, which one will be reactant. Okay, and finally, yes, you will get some representation as this. This is just an example. It's not something for you guys to memorize or what. I mean, as I said, it's just to show you where Nernst equation can be applied. Okay, right. So as I mentioned to you guys last Tuesday, the function of reference electrode previously was to measure potential. Measuring potential. So all cell potential measurement requires at least 2 electrodes. Okay, so it can be either working electrode, okay, to reference electrode, or maybe you can also need 3, but at least you need 2, because as I said, working electrode will produce potential, and this potential need to be read by reference electrode. So any measurement that want to confirm the overall cell potential, okay, it must have this pairing, working electrode to reference electrode. You will use a voltmeter normally to read the potential values, but sometimes if the voltmeter is considered too classic, then people will just put it together with a machine like potential stat or whatsoever. Imagine that if you are dealing with silver chloride, so silver chloride, and then mercurous chloride. So anyone knows mercurous chloride function as what? I think I explained to you guys last Tuesday. Where can you find mercurous chloride? Anyone knows? Madi? If you still can remember?
It is in galvanic cell.
In what?
Galvanic cell.
Okay. How about where do you think that you can find mercurous chloride?
Thermometers.
In what?
Thermometer.
Thermometer. Thermometer. Mariam? I mean, if we are talking about electrodes, I think previously I've mentioned where you can find mercurous chloride in electrode, and what kinds of electrode that we call that?
STE.
Sorry?
STE.
Yes, correct. So if you remember, for reference electrode, we have standard hydrogen electrodes. We also have saturated calomel electrodes. We also have silver chloride electrodes. Okay, so all these are actually giving different accuracy whatsoever. But what makes special for saturated calomel is that we are using mercurous chloride as one of the components. So remember, in the anatomy of saturated calomel electrodes. You have a platinum wire or silver wire connected into mercurous chloride. Okay, and then you have like a porous material over here, a septum over here, and inside this electrodes, it will be filled with potassium chloride. So the reason why we use mercurous chloride is because the features or the properties of mercury, because it is in the form of amalgam, it's a semi-solid. If you look on the dimension, it's more of like a spherical. Then the ions that penetrate or absorb into the electrodes, it can be attacked at any direction. Imagine if you use silver chloride electrodes. Okay, you have a silver wire, just a silver wire over there, and the septum over here. Then the dimension of the silver wire will be like cylinder. Okay, cylinder. So the attack or the interaction between ions to be absorbed or to be detected at this surface area will be oriented as compared to mercurous chloride, because mercurous chloride, as I said, is spherical, so you can attack it at any side. So this giving more accuracy in terms of giving potential values, right? So then you will have Nernst representation for the anodic reaction as this, okay, and you also have the Nernst representation for your cathode. Okay. So this representation is noted by, okay, you will see over here that the E cell is equals to E naught cell plus 0.059 over N log 1 over product. So product over here is Cl minus, and remember that solid is the reactant. So normally solid within or solid doesn't have any concentration or activity. So that is why it is noted as 1. Okay, right. The same thing over here. Okay, the product is actually chloride ions. So chloride ions actually plays an important role to affect these potential values. And while for mercurous chloride, it exists as solid, and solid normally we didn't count it as concentration. Right. So as I said, N is actually referring to the number of electron transferred per mole. Right. So for electrochemical cell, this of course the same, almost the same examples that I've shown before this. So you have a cell notation as this, okay, and you know from this representation which one will be anode, which one will be cathode. Okay. Over here, zinc is far more negative as compared to copper. Okay. Then you'll see zinc, when it is oxidized, it will form zinc 2 plus. Okay. Zinc 2 plus 2 electrons, okay, as an anode, and then for cathode, this is actually the reaction. Okay. So notation over here, double slash actually means that you have a salt bridge. Okay, the solution is actually separated with each other, and salt bridge is also functioned to make the cell. And over here, the reference electrode used is what? Anyone knows? Looking at the diagram, what kinds of reference electrode that they use to measure the potential value? This is a standard hydrogen electrodes, because you see over here you have a hydrogen inlet, and then this is actually the platinum plate. Okay, right. So far, is there any question? I mean, related on Nernst or whatsoever? Anything?
Doctor, can we use the law is E cell equal E anodes plus E cathode?
For this one?
Or in general?
In general,
Yeah.
as I said, if the experimental condition is in the standard condition, then no problem. Standard condition, pressure 1 atm, concentration 1 molar,
Yeah.
temperature 25 degree, then it's okay. But if it is not
Not standard, we
the
have to
same
use the
parameter,
Nernst
then you
equation.
have to use Nernst. Yes.
Yeah, okay. Thank you.
Okay. All right. So this is just other things related on electrochemical cells and reaction. Of course, the electrode can be noted as a conductor, and electrolyte is actually ionic solution. As I mentioned, it will be an aqueous solution where the water normally dissolve the salts and it become an ionic solution. It become conducting solution and used as a electrolyte. So you can find electrodes at many types, like platinum, gold, palladium, carbon, mercury, and whatsoever. Okay. And electrolytes can be noted as a lower ohmic resistance. Lower ohmic resistance means that it is a very highly conducting solution. Okay. For example, like ionic salts, molten salts, and ionic polymers. Electrode kinetics are affected by the electrode surface cleanliness, surface microstructure, and surface chemistry. That is why it is important before you conduct any sort of electrochemical measurement, you need to polish the electrodes, either glassy carbon, plates, or whatsoever. The reason is because on the surface, probably there's a formation of a passive layer, oxide layer, or there's any corrosion resistant products on the surface, oil and whatsoever. Then to have a very good values of potential or current produced, you need to clean it and make sure when you do the cleaning, it is homogeneous. Okay. Right. So the two electrified interface, but one is actually of interest. Of course, when I talk about the interaction or the interface between working electrodes with reference electrode, you will see that the process is most likely to occur over here. The charge transfer, the mass transfer process, then this will create an interface. Okay. So this interface will determine the rate of redox process, and sometimes you can actually see what kinds of phenomenon that will occur on the surface of the electrode. Either there's any like coating, or there's any diffusion process and whatsoever. Then the phenomenon can only be monitored using electrochemical methods. I believe this one is almost the same as what I have explained earlier on the electrode process. So I think we'll skip this one. All right. So all the while we are talking about the cell notation, but we have not come into an example. Okay. So as an exercise, I guess maybe for the mixed mode student, you can do this as part of your homework. So exercise 1, write the cell reaction and the half reaction, anodic and cathodic, of the represented cell. Okay. So if, like for example, the question is asking the cell reaction, then what you need to do is to write the half reaction. For example, for A, you'll see over here, platinum and hydrogen. So if you still remember what I have told you before, if you have platinum and you have a gas, then you know that for this process, this will be anode or cathode.
Will be anode.
Mariam? Sorry? Madi, you say anode. Mariam, what do you think?
Cathode.
Cathode. Hamda?
Wait.
Hamda, do you have any idea?
Yeah, anode.
Sorry?
Anode.
Anode, okay. So Madi and Hamda say it's anode. Liana?
I think it's an anode.
Anode too. Shamira?
It's anode, Doctor.
Anode juga. Okay, alright. Bukan anode pelakon tu Okay, alright. So, if you still remember, I've told you that if there's any production of gas, especially hydrogen gas, okay, then this one, okay, will be cathode. Okay. So I'm taking example of exercise 1A. Imagine that you have this one. It says that you have silver, connected with platinum. What types of electrolyte that they use? You can get some clues over here. You can see that it is mentioned over here that they use HCl. Okay. Between silver and platinum, which one do you think that is more reactive? This also can give you an indication which one will be anode, which one will be cathode. Which one is more reactive? Of course, if you refer to this electrochemical series, silver is more negative in terms of the standard potential value. So this will be anode. And platinum, always remember that this is a noble metal. It is less reactive. So anything that is related with the connection with a less reactive electrode will always going to be cathode. Okay. Right. So this is hydrogen gas bubble. Okay. So then how we can write the half equation? So since you already know that this will be anode, this will be cathode. Okay. So for anode, the reaction will be silver plus electron. And for cathode, okay. So what kinds of half equation that you should read? You should write. It is not on platinum because platinum, as I said, is an inert electrode. Then how the cathodic process looks like? It is actually by the formation of H2, okay, from this one, HCl, because HCl actually it can be dissociated into H plus Cl minus. Then the reduction process will be 2H plus 2 electrons, then okay, it will be H2. You can balance the equation. If you want to balance the electron number, then you can have the overall. So just okay, is 2Ag plus 2H plus, okay, 2Ag plus H2. Right? Any questions so far? Anything? Can you get it, Mandy?
Yeah, yes, doctor.
Okay.
Thank you.
If you look to another examples, 1B, you'll see that the electrode used over here is platinum. Both are actually platinum and platinum. So what is actually happening? I mean, what kinds of reaction that happens here? Okay. If I ask what types of cell that being used in 1B, anyone can try. Anyone knows?
Galvanic.
Galvanic. Siapa ni yang cakap? Nazira. Nazira. Nazira is guessing it is galvanic. Okay. How about others? How about Shamira?
It's galvanic, doctor, because using two different electrodes.
Oh, really? Okay. Galvanic. Okay. And then Liana, sama juga. Liana, what do you think?
Boleh jadi elektrolitik sebab dia PT-PT?
Yeah. Actually, you can see the clue is there because the electrode used over here is the same types of electrode, platinum and platinum. So of course, if you refer back to the definition of electrolytic and also galvanic cell, I told you for electrolytic cell, it use two similar electrode and the electrode used must be inert. Okay. So in this case, this process is basically electrolysis. So you can imagine that, okay, they are using platinum, okay, maybe positive, negative, okay, and then maybe over here, oh, sorry, my mistake, okay, there's a septum, okay, and then there's like maybe salt bridge or whatsoever. Then you have over here is actually either FeCl2 solution, and this one SnCl2 solution. Okay, so either one will experience oxidation and reduction, but the oxidation and the reduction will depend on the terminality of your supply. Okay, then if I ask you which one will become anode and which one will become cathode over here, if you check, anyone knows? And how we can determine which one will be anode and which one will be cathode for this kind of reaction, anode or cathode? Can someone?
Zinc will be anodes and Cl2 will be cathodes.
Okay, Mehdi is guessing. You are guessing FeCl will become anode. Fe will become anode, and the tin will be cathode.
Yeah.
Okay. Any other suggestion? Anyone?
Anode and cathode tu boleh juga depend on the yang tengah-tengah tu, yang panjang yang pendek tu. Boleh tak?
Panjang pendek, sorry.
Yang macam dekat gambar bateri yang terbulat tu.
Okay. That one is I just draw the examples, but of course, in order to know which one will be anode, which one will be cathode, for B, you have to consider something.
From ECS?
Yes. Siapa? Mariam?
Nazira.
Nazira. Nazira, sorry. Saya jadi confused Mariam dengan Nazira. Suara lebih kurang. Okay. Basically, you have to check on electrochemical series, even though it is a electrolytic cell. Okay. So that is why I think for this kind of setup, it is important to know which one will be anode or which one will be cathode. Otherwise, the experiment cannot be proceed because you put the chemical reactivity wrongly. Okay, all right. So how you can determine that? So basically, if you refer to a full range of electrochemical series, you can actually look at over here, okay, Fe2 and Fe3, because this one FeCl2, FeCl3. So this one means that it is from Fe2 plus, okay, and then we become Fe3 plus, okay, Then another one will be tin 2 plus, and then it becomes tin 4 plus. Okay, right. So you can check the electrochemical series. What will be the standard potentials value for these two types of ions, and later you can determine which one will be anode and which one will be cathode. Is it understood? Boleh faham? Is it okay?
Yes, Doctor.
Okay.
Yes, Doctor.
All right. So I hope that you can try to do this as part of your homework. Okay. So exercise 1 and exercise 2. So exercise 2 is in opposite because it gives the overall reaction. Okay. And they ask you to write in a notation. Write the cell representation or notation for the following reaction. So I'm taking example 2A. So you have zinc plus with copper sulfate producing zinc sulfate plus copper. So this easy. Even you know that okay, the from this reaction, okay, the anode will be zinc and then the cathode will be copper. So the cell representation, of course, it will be zinc slash zinc 2 plus. Okay, then you have a slash like that. Okay, 2 plus slash copper, for example. Okay, and the rest is also the same thing. All right. Except if you notice, if there is any formation of gas, as I said, gas, this one, like for example, H2 for reaction, and this one you have H2 and O2. Then what types of electrode that you will use? I think it's I have explained it earlier. Samira, what do you think? The types of electrode that we will use if you have the reaction that produce this?
Is it platinum, Doctor?
You can use platinum or you can use graphite also, no problem. Okay, but I think like normally we use platinum. I mean, but if you write graphite also, I don't say it's wrong because it's also in it. Okay, so meaning that over here, okay, you know that from this reaction, okay, you have silver, okay, and then it become silver ions, and then this one will be acid, and it becomes H plus. So from here, the equation is a bit haywire. You might be confused. You say, okay, actually the anode is acid because this one Ag plus will form Ag reduction, but the answer is actually no. If you notice over here, okay, the arrow indicates that this process is reversible. Reversible means that it is a two-way process. So it can be either Ag plus HCl in front, or it can be back also. No, I mean like no worries. But in this case for B, of course the anode will be silver. Then you know, okay, Ag, okay, we got Ag plus, and then this one will be HCl, H plus, and then this one will be what? Platinum, for example. Then this will be your cell notation. Okay, right. So the others, I think maybe you can do it by yourself. Even for C, this one is actually electrolysis of water, because it produces hydrogen gas and oxygen gas. Then you can actually try to write the cell notation for this one. See, but things that you need to remember that if you have any gas formation, then you should use either platinum or graphite as the electrode. And you can also take note that if you have produced hydrogen, or the product is one of it is actually hydrogen, then this will always going to be cathode. Okay, because remember, cathode means that the process is reduction, And reduction is always the formation of what? Hydrogen gas and whatsoever, not the production of oxygen gas. Production of oxygen gas will be oxidation, and oxidation is always related to anode. Okay, is it understood? Boleh faham? Hamda, is it okay for you?
It's okay.
Okay, so please try to do this. I think later after this, I will create an event in the e-learning, so you can try to write it and maybe submit in the e-learning. You can like snap the photo, or I mean, make it into PDF or what, and then submit it in the e-learning. Okay, and probably next week we will discuss on this exercise. All right. So another examples. Okay, this is actually the examples how you can calculate the cell potential. Okay. One of the most important reaction for the corrosion of iron in acidic medium is iron reacted with acid, okay, and oxygen to produce Fe2+ with water. What is the spontaneous reaction direction if the activity of Fe2+ is equal to AH+ equal to 1? Given that, okay, the half equation for Fe is cell potential is and E naught is equals to minus 0.44 volt, and for the production of water, the cell potential or the E naught is equals to 1.229 volt. All right. So of course, from here you can see that the reaction comprises the two half reaction. Which one will be anode? Which one will be cathode? Anode will be Fe because the cell potential E naught is more negative. Okay, then you know that this will be oxidation, experience oxidation. Then if you want to write, okay, if you want to calculate the E naught cell, then it will always be this one is reduction, this one is oxidation. Is actually the formula. So E cell, you substitute 1.229 minus with minus 0.440. Remember, as I told you, don't actually change, even though this is actually in a reduced half equation. Don't actually, change the sign, the symbol or the sign, because you said, okay, now the half equation will be Fe becomes Fe2 plus 2 electron, then I should also change the symbol. No, for this formula, you just use as it is in the reduced form, and you will get minus with minus is equal to plus 1.669 volt. So the overall reaction occurs, okay, from left to right. Okay, from left to right means that left is because this process is actually oxidation producing electron. Then this electron will be later on passed into okay, the cathodic side to proceed with reduction process. So that is why I think it says the direction will be from left to right. Okay, so left from product, okay, to reactant. Okay, any question so far? Anything you want to ask?
So far okay, Doctor?
Okay, for example 3, calculate the equilibrium constants at 25 degrees C for the reaction of zinc plus chloride gas, okay, that forms zinc chloride using the standard electrode potential as shown follows. Okay, so same thing. You look at the half equation, the electrochemical series. The E naught is equal to 1.35. Okay, for zinc is equal to minus 0.7. And then Right. So since for this one, okay, the reaction is as follows. Okay, the K equilibrium, okay, is equals to, okay, product over reactant. This is actually product. So the product actually tells that it is the formation of zinc 2 plus with, oops, 2 chloride ion. Okay, and this will be the reactant. Products. Okay. So the K equilibrium is actually related with the activity of the product over the activity of reactant. Because the question actually asks the equilibrium constant. So equilibrium constant is actually equals to K. Okay. So you just substitute over here, then you will see that K is equal to activity of zinc 2 plus multiplied with activity of Cl minus, and remember over here you have a stoichiometry that is equals to 2, then you need to square it, you need to make it a power of 2 over the activity of the reactant, which is in this case zinc, and then multiply with F Cl square, because it is exists as Cl2. Okay, so anyone knows what is mean by F? Initially, we know that A is equals to activity. What is F? Anyone knows? Anyone knows? And when we should use or address it as F? Mahdi?
For the product, not for the action.
Okay. Thank you.
Yeah, welcome.
How about others? Hamda, what do you think? How do you think, Hamda?
It's for the product.
Product, not really. Okay. Shamira?
I think it's for the gas chlorine.
Okay. You almost got it right. Okay. F is actually means fugacity. It is not activity. Okay. Fugacity. Okay. So fugacity is always related with gas. Okay. So that is why over here you see that, okay, gas, chlorine gas, then we cannot use activity because gas doesn't have any concentration, isn't it? Okay. So we use fugacity lah. And normally fugacity will not going to be account for the Nernst or any effect on equilibrium. Later on, it is negligible. I mean, we can cancel it off. We'll see it later. Okay. But just to let you know, A is actually refers to activity of ions, of solid or whatsoever, and F is fugacity for gas. The reaction can be written as the half reaction. Then you will actually see this. Okay, for the right reaction, okay, at the reduced form, you see this is actually the equation, and when you represent it as Nernst, then you will see that, okay, E naught is equals to, sorry, E cell is equals to E naught minus RT over F ln activity of product, which is activity of Cl over F Cl. Okay. So half, it means that the this one, the stoichiometry, yeah, is power to half. And then the left hand side, okay, the oxidation process, this is the half equation. Then when you write it at for Nernst representation, you will get E cell for oxidation is equal to E naught oxidation minus RT over F ln activity of a product, which is zinc, over the activity of zinc 2 plus. Okay, power of half. So at equilibrium, where the reduction potential is equals to the oxidation potential, then you just rearrange the two half equation or the two Nernst representation, you will get this. Okay. So yeah, I mean, for this one, actually you can calculate it. Okay. Because this one is actually calculated from value. 1.6. Oops. .7, I guess. Then you get something like 2.1 something, isn't it? Is it 1.6? Sorry, 1.35, 1.35 and 0.7, 1.35, 0.76. Should erase it. Okay. Another one. Okay. Then you will get such value. This one. How about this one? I mean, since this can be considered as K, okay, then it will be ln K. Then where, I mean, 2 comes from? Anyone knows where the 2 is actually comes from? Okay, the 2 is actually coming from the cancellation of this one. Okay, so if I multiply it with 2, so this can be cancelled, it will be 1, okay, and this will be 2. So that is why it will be 2F. Otherwise, it will be like 2K lah, 2K over here. Okay, so I just bring it here. Then because it's ln, and when you bring the values over here, then it will be 2. Then this is actually the value. So R, the gas constant that you can use is 8.31. For okay, temperature 298, okay, or Faraday's constant 96,500. So when you substitute all together, you get K is equals to this value. Is it okay? Did understood? Okay, you guys can follow or no?
Okay, Doktor nak tanya satu benda. I wanted to ask. The one that you times 2 just now, you said that it become 2K. It's bukan dia K over 2 eh?
K over 2?
Doktor kata kalau dia tak duduk di
Yeah. Sorry.
Okay.
Yes, but yeah, betul. Dia akan jadi this one we will multiply with 2, so it will be like 1 over 2 lah, 1 over 2K.
Yes.
2 over K. Okay. Sekejap. Yeah. As I mentioned to you earlier, okay, for gasity, this one we will cancel off, okay, and this one also we will not consider it, we consider it is equals to 1 because this is actually solid. Okay. So since we have a power of half, because the equation is written like that, I mean, and we use like 1e, so I just multiply it with 2, and then this will be 1, and this one will be like 2 lah. I mean, like multiply with 2, and then if you remember, I mean, like ln 2, and then this one is RT over F, okay, multiply with ln. So if I want to bring the K, I mean, or the 2 over here, so I have to make it an opposite lah. So that is why it will be like 2F instead of like 2RT, because it is actually in ln representation. So if I want to like remove it out, so just like make it opposite, then yeah, then it will be 1 over 2 lah instead of 2. Is it okay?
Doctor, why K puts power half? Should be power 2.
Why K?
Yeah,
Power
this,
half.
yeah.
Which one, Madi?
A activity Cl minus multiplying AZN plus 2, all of them power half.
Oh, no. This one is not the, yeah. It shouldn't be like that. No. This one should be half. You get what I mean?
Yeah.
Right. How
Because
about we just write the notation again? Okay, so the reduction half equation is half Cl oops, isn't it? Oh no.
Yeah. Doctor, in this case, I have to use N is half, not 2.
N is half.
Yeah, and is 2 2 multiplying F and the Nernst law. We should use in this case, if I put half in the half cell reactions, I put half, not 2.
Okay, so never mind. We'll do it together. I mean, like probably you guys might be like wondering how we can get something like this. Okay. The reason why I put like all together it's equals to like half, because if you see over here, this, okay. So the activity of your chloride ions and zinc plus, also for the product, which is the Cl2 and zinc, it's actually the power of half. You can make it 2 actually if you think that half is a bit confusing. But of course, over here, then N will be equals to 2 because the number of electron that will be considered is equals to 2. I mean, if let's say I just make this into Cl minus plus 2 electron I guess maybe there's something wrong. I mean, in the half cell notation. This one is okay. This one, because this one actually produces only 1 electrons, and so did you ask me like why Cl is power of half, Mehdi?
Yeah, because you use in the K half, but when you apply it in N and F, you apply
Mhm.
2.
Yeah. So I get you now. Because when we write it something like this, you will see that, okay, for zinc, if we just make it into 2 electrons, okay, because zinc 2 plus, then this would be like only 1, right? So if I make it like half, then this one will be like 1 electron, this one will be half. But for this one,
And should be half like so.
yeah. So actually, there's a problem. I mean, in terms of like yeah, the mistake is actually this one half 2. Yeah, that's correct. So never mind. Actually, just to let you know that when you guys use this, like for example, this one, 2 chloride ions plus with 2 electron with Cl2, and this one, the numbers of electron involved is equal to 2, and then in the Nernst, you know that it's RT over NF, and N, that the values that you will use over here is equal to 2, then yeah, you will substitute it into 2. The reason actually, as what I told you, if we use half and we multiply it with 2 and we bring it forward, then this will be like 2. But this also the same thing as what if I change it to 2 electrons initially without like doing it half. Then I guess by doing it half, maybe it's kind of hard for you guys to understand, because later on why we need to multiply it with 2. But actually the reason is because we don't want it to, I mean, make it into a power of half or what. So then if we use this as usual, like 2 electrons, then the n is equal to 2, then it solves the problem. Then you will get this one. Okay? Is it okay? Mayu,
Yeah.
Adi?
Yeah, okay.
All right. Okay, so we are moving on to activity coefficient. So all the while we are talking about how activity affect the potential of the electrochemical process. Activity coefficient is basically determined for every types of ionic salts or ionic compounds. Okay, so there's no direct way to measure the effect of a single ion in a solution, because it's always in balance condition, charge balance. You have one positive, you have another counter ions, it's also one negative, and then the mean ion activity coefficient will actually determines for salt. Okay, so because salts normally exist as a charge or a balance salt, okay, then the symbol that is used for activity coefficient is equals to gamma. Okay, so gamma of KCl. So KCl salt, when it dissociate in water, it become K plus and also Cl minus. Okay, so you have to consider the ionic the activity coefficient of K plus and also activity coefficient for Cl minus. Then this is always related with KSP. So KSP is a equilibrium constant for salt. Right. So that is why you have that kind of representation, lambda plus minus KCl, okay, multiply with mk plus. M is actually the concentration of K plus. Small m is actually molality, okay, and MCl is actually the molality of Cl minus. All right. This is just to show you how ionic strength will give a difference in terms of ionic coefficient values. So over here you have a different types of salt, ranging from NaCl, KCl, copper chloride solution, sodium sulfate, potassium sulfate, and also copper sulfate solution. If you notice over here, okay, the y-axis is actually the ionic activity coefficient. Meanwhile, the x-axis is the ionic strength. Okay, right. So if you see over here, okay, ionic activity coefficient will increase, okay, as the ionic strength is higher as well. Okay, all right. If you compare between sodium and potassium, because these two is actually from the same group, which one is having a lower dimension or a lower atomic radius? Anyone knows? Between sodium and potassium, which one will have a lower atomic radius in terms, I mean, in terms of atomic size?
Potassium.
Sorry,
Potassium.
potassium. Potassium. Who's this?
Oh, Mariam.
Mariam. Mariam says sodium actually have a sorry, potassium have a lower, smaller atomic size. How about others? Hamda, what do you think between sodium and potassium? Which one having a smaller atomic radius?
Potassium.
Potassium. Still the same thing.
Yeah.
Sodium has.
Sorry?
Either higher or lower?
Lower.
Lower sodium.
Correct. I think Mahdi answered it correct. If you notice, group 1, lithium, sodium, potassium, okay? As you go down to this group, this is actually group 1. Okay? Group 1. As you go down to group 1, the atomic radius will be increased.
Okay.
Increase of atomic radius. So what happens actually if you have an increase of atomic radius? What do you think about the ionic strength? Is it going to be easy to repel or what?
The ionic strength will be weaker.
So the ionic interaction strength will be decreased as the atomic radius increase. Okay, so lithium is always one of the best conducting material because the atomic radius is smaller and the atomic or the ionic strength is greater. Because normally for a smaller size of atoms, the smaller it is, maybe the ionic strength is even greater. Okay, so that is why if you notice over here between sodium and also potassium, the chloride is the common ion. Okay, you'll see that for sodium chloride, it has higher ionic activity coefficient, okay, as well as the ionic strength is also higher as compared to potassium chloride. What about copper? Because I think copper, if you compare it, copper is in the transition state. The atomic radius for copper is even bigger as compared to sodium and also potassium. So, as I said, atomic size increase, then you will have a decrease of ionic coefficient and also decrease of ionic strength. Okay. And if you compare with sulfate, because sulfate okay, so sulfate is actually a more complex polyatom. Okay, so that is why I think for this one, the atomic or the ionic strength is even loose or not as if you use only like chloride. Chloride is also like smaller in size. I think it's monoatomic. Okay. So that's why I think the trend you will see over here, if you have a polyatom ions, then it also can contribute to a lower ionic coefficient and also ionic strength. Okay. Right. So when we also talking about ionic strength and also activity and
Sorry, I'm trying to connect my
ionic
Bluetooth.
coefficient, you cannot run away
I'm trying to connect my
with
Bluetooth.
a
Is it disturbing?
Debye-Hackl theory.
I'm trying to connect my Bluetooth. It's not.
I hear a voice. Franklin, can you mute your mic? Very sorry, I hear your voice. You're talking to your friend maybe. Okay. So we cannot run away with Debye-Hackl theory. So Debye-Hackl theories actually relates activity coefficient with ionic strength. Okay. So of course, I think during undergraduate, those who are taking physical chemistry may learn about how to derive the Debye-Hackl equation. It's a very long equation, and as I said, it is not something easy for non-science student to understand the story behind it. Is because it's more of like physics and others. But the Debye-Hackl equation, I think at the end you will get this: log gamma is equals to minus AZ. Okay, AZ square cert A. Sorry, cert I. So this is actually equation that assumes the ion interaction, and if the ion size does not vary with the ionic strength, then the ions of the same sign will not going to be interact. So we also have the extended form of Debye-Hackl. Okay, so extended forms of Debye-Hackl is sometimes considering other factors. Okay, not only on the ionic strength and also the coefficient, but also another factors which also related with the mass, for example, mass of the salts and whatnot. Okay, all right. So the component of the Debye-Hackl equation, okay, you have A and B. A and B is basically a constant values, okay, which normally derive from the dielectric properties. Okay, and normally we use a reference, and the types of reference is water. Then you will see that for A and B, the dielectric constants of water will be as follows. Okay, 1.82 okay, multiplied with 10 power of 6. Okay, and rho is actually the density of water. Density is water is equal to 1. Okay, right? And yeah, for one ions, okay, the charge is carried by one ions, and gamma is the activity coefficient, and capital I is actually the ionic strength. Ionic strength is actually equals to half to the sum of mz squared, which is m is molality, the concentration in molality, okay, of I in ionic strength. I think later on we will see the examples how we can calculate ionic strength, okay, using this formula. Right, I guess for this one, probably if you have some time, you can see how you can derive Debye-Hackl, but I don't think that it is something that you need to memorize or what. It's just for your information, how you can get those, I think, representation. Okay, because this is actually considered a basic knowledge. You have learned it during undergraduate. So yeah, if you have time, you can revise back how you can derive Debye-Hackl from the internet. Okay, right. So for the examples, you have this one. Calculate the ionic strength of 1 molar potassium nitrate, potassium sulfate, and potassium ferric cyanide solution. And the ionic strength is defined as capital I is equal to half to the sum of concentration multiplied with charge square. Okay. So for potassium nitrate, when you dissociate this salt, it will form potassium plus with nitrate ions. Okay. So if you see over there, the charge or the ions produce 1 for K plus and also 1 for NO3 minus. Then the ionic strength will be as follows. I is equals to half multiply with 1 plus with 1 square. Both is actually you make it square, and then if you plus 1 plus 1, 1 square is equal to 1, 1 plus 1 is equal to 2, 2 multiply with half, you get 1. For potassium sulfate, okay, potassium sulfate, when it dissociates, it forms 2K plus SO4 2 minus. And then if you want to calculate the ionic strength, it will be equal as capital I is equal to half multiplied with 2 times 1 square. So 2 is actually coming from the stoichiometry. Okay, multiply with 1 square. 1 square, why it is 1 square? Because potassium produce 1 ion, 1 charge. Okay, make it square. Okay, plus with sulfate. Sulfate have 1 mole. Okay, plus or multiply with 2 square because the charge is equals to 2, so you just make it square according to the formula. So altogether 2 square is equal to 4, 4 times 1 is equal to 4, plus with 1 square is equal to 1, 1 times 2 is equal to 2. So then 2 plus with 4 is equal to 6. 6 multiply with half, you get 3. Okay, all right. I hope it is okay for you guys. And then the last one, okay, potassium ferric cyanide. You see that the ionic strength I is equals to half. Okay, 4 multiply with 1 square. So 4, why 4? 4 is because of the stoichiometry. When it dissociates, it forms 4 moles of K plus and 1 mole of ferric cyanide solution. Okay, and then plus with 1 multiply with 4 square. So 4 square is equal to 16. 16 plus with 4, then you get 20. So 20 multiply with half, then you get 10. Okay, so is it okay to everyone for the ionic strength?
Okay, Doctor.
Okay, so I guess probably for others, for this example, because this is actually how we can apply Debye-Huckel in the current scenario, how you can actually calculate, okay, the potential, the electromotive potential, okay, when you have a different concentration at the different potential values. Using Debye-Huckel, this can give you some indication, but I guess this one maybe you need some time for the explanation. Then we will continue this part next week. Okay. I guess if you guys are okay on Tuesday, I would like to do a quiz. Okay, it's an online quiz. I will later on post the question on the e-learning, and then probably we will see whether you can understand or not. So the question is more or less on chapter 1, okay, which we are currently look at, probably on the introduction of electrochemistry definition and whatsoever, and then probably some question related on the cell notation and how to write a half equation or something like that. Okay, so Is there any question before I call for the day for today? Anything?
Doctor, is
Yes.
this the rule of the vehicle, the previous one, the slide, no, yes, this
Yes.
log y is equal minus a z I square multiplying I. Is it for one ionic or two ionic?
Okay, this one is for one.
What?
This one is for one type of
For one.
species. So
So
this is why
okay,
you
if I
have two, because you have like the other one, which is on your right. This is actually if you have a two species of active compound that produce charge.
example the law one, the first law or not?
Yes, if you want, if you have a KCl, then you will use this one as a formula. I mean, in the formula to calculate the
Yeah, but I will put
ionic coefficient.
minus.
Sorry, what again?
I will add the log y plus minus is equal a minus z I plus minus multiplying I square root.
Yes, yes, and you need to find the ionic strength for KCl first.
Yeah, and I have to use this rule, this law twice, one for K, one for Cl.
No, no, no. You will use it only once for both.
For both.
Yes, because the charge is equal, and you only have like KCl solution. So you, as I said, the ionic strength will be calculated for KCl, not the ionic strength. Well, you cannot calculate ionic strength for individual, I mean K plus or individual Cl minus.
Because ionic strong we will use one time, but for Z we use two times because we have to charge.
Yes, but I think the point is because the charge is equal to one, then if you use
If
either like one times or two times, it's still the same thing because I mean like one square will become to one. If you split it into like k plus for this one z, and then you use cl minus for z minus, then still I mean it's the same thing because at the end you just plus one to one.
the clarify has two charges, different charge. For example, minus one and plus two or minus two. Can I use the same law?
Uh, for that kind of things, if you have like potassium sulfate, because sulfate have two
Yeah, and
electrons,
potassium has one.
okay, then you will split, but you still use this one, this formula. I think this formula that has A and B is where when you have two electrolyte, you have KCl and the same time you have another solution. Normally for galvanic cell, because galvanic cell you have individual electrolyte solution, then you have two electrolyte that actually contribute to the potential difference. So that is why I think for that one you have to use this one, but for only one type of electrolyte species, then you have to use this one. So back to the question, you said if you have two different charge from one electrolyte, like for example now potassium sulfate, then yes, you will split the Z.
Yeah. If I split the Z, I can use for different charge.
Yes, yes.
Okay.
Okay. All right. I mean, later, Mahdi, next week, we will see the examples. I mean, later on the Bahaka and things that you asked just now. Okay. Any other things you want to ask also, Mahdi? About others? Hamda, are you okay? Oh, I just noticed. Yeah. Dr. Ridwan is here and Dr. Hashima is also here. Welcome.
Hi.
Okay. We have not started with corrosion yet. We just, started the lecture this week. So we go through the basic physical electrochemistry before we go to the high end. Okay. How about Mariam? Do you have anything to ask? Anything that you are not understand?
No, doctor.
Okay. All right. So the rest, I guess, if you have any problems, you just let me know. In our WhatsApp group. So as I mentioned, you have one homework to do. Is actually on which one? Just now. Yes, on this one. Writing of the half cell reaction and also the representation. Okay, the cell representation. Okay, I will create an event in the e-learning later on. So you just write through on a piece of paper and you can snap the photo and make it into PDF and submit into the e-learning web. And I think next Tuesday also we will have online quiz. Okay, so basically it's more of like what we have studied for this past 2 days. Okay, and for the examples of this one with debug hacker, we will continue it next Tuesday. So with that, I will call for the day for today. Thank you very much, guys, for your kind attention, and I'll see you next Tuesday. Assalamualaikum warahmatullahi wabarakatuh, and thank you.
Okay, have a nice day.
Thank you, Doctor.
You're welcome.
Thank you, Doctor.